Greetings, chemists. It's Mr. Gopal here with a very special lesson on balancing equations. So I share my screen. I'm just going to talk about some of the utilities of balancing equations. This is from Unit 6, Day 14. Our focus question is, how can we use a simulation to practice balancing chemical equations? You're going to use the simulation, but you're also going to make use of a cheat sheet I made especially for you. And I'm just going to talk through some of the nuts and bolts. But first of all, let's break down what balancing equations actually is. So what it actually is thinking about producing a chemical reaction that results in some sort of change to the compounds involved or the elements involved, resulting in new compounds and or elements. So I'm going to show you some of the examples here. All right. Now, what I want you to do is see if you can pause the video and think back to earlier in this unit when we were talking about types of chemical reactions. So we've got A plus B turns into AB. We've got AB turns into A plus B. And then we have AB plus C turns into AC plus B. Finally, we have AB plus CD turns into AD plus CB. All of these reactions, these four reactions, are four different types of chemical reactions that we categorized earlier in the unit. All right. Each of A, B, C, and D represent different elements. Okay, so we see different combinations and outcomes happening in every equation. Pause the video right now and see if you can name each of the four types of chemical reactions. Okay, so how'd you do? All right, think about it, and I am going to name each one of these on the side right here. So this first type, where we have A combining with B to make AB, that we call a synthesis. All right, and I like to think synthesizing is creating something new, and that's when we bring elements together to form a compound. All right, elements combine to form a compound. The next one, we see the opposite thing happening. We see AB breaking down into A plus B. We call that a decomposition. Right? That is when compounds break down to form elements. This third kind, we see AB plus C turns into AC plus B. So one of the elements is exchanged for the lone element, and that becomes a lone element, and the other element combines with the previously lone element to form a new compound. Since one thing is being replaced by one other thing, we call this a single replacement. So a single replacement, one element in a compound is exchanged for another. All right, and now finally with the last one, we have two different elements being exchanged in two different compounds. All right, so they kind of trade. Each compound trades one element for another. And as you might predict, given that the previous one was called a single replacement, this is called a double replacement. Elements in compounds are exchanged. Okay, so two get exchanged, resulting in two new compounds. So hope you did well on that little pop quiz. All right, I'm going to leave this up for a second so you can copy it down. And while I leave it up, let's consider what the utility is of balancing equations. Let's say that you work in some sort of chemical lab and your task is to produce some sort of new compound. Let's say you're making a detergent and you need to combine certain elements to make that detergent, and you need to make sure that you combine it in the right ratio so that it's healthy. All right, we're talking about a detergent here that is not kind of an active danger to people who are using it. All right, it's not going to, let's say, produce an allergic response on your skin. It's just going to wash clothes, and it's kind of environmentally safe. All right, so we really need to make sure that we get the ratio right. But when elements recombine, sometimes they combine in different combinations or ratios of atoms, okay? So you might see a compound that is like 1-to-2 ratio of certain atoms, and then a lone element, let's say it was a single replacement. And in the chemical reaction, we produce a new compound consisting of one of the elements in the previous compound and the lone element. And now that other element that was in the compound previously gets broken off. But because of the valence electron structure of each of the elements in the new compound, the ratio of atoms is different, okay? And so we need to realize how much of the new compound we're producing. This gets into a little bit of stoichiometry, which we're going to explore in further videos, all right? And the basic idea here is that we're going to produce a certain amount of moles of the new element versus the old one. And that number of moles of the new element versus the old one, or I guess you could say the ratio of moles from the reactants, which is what we started with, to the products, which is what we end up with, that ratio is going to be very important to making sure we produce the right amount of a safe detergent, okay? So as you can see, balancing equations is super important. I'm gonna clear this screen, all right, and just give you a sneak preview of this simulation, all right? So what you're doing in the lab is you launch the simulation and you have to remember the law of conservation of mass. So before we get into balancing, I'm going to review the law of conservation of mass. This is one of those handy laws that is exactly what it sounds like, all right? And that is that the amount of mass in the reactants in a chemical reaction must equal the amount of mass in the products of a chemical reaction. In other words, here is the gist of it. Matter is neither created nor destroyed in chemical reactions. It merely changes form, okay? And so that's like the heady concept. The practical application of that is we need to have the same amount of molar mass on left and right to make sure that we have the same amount of stuff, essentially. And that is our guiding principle as we balance these equations. On to my sheet, all right? So this sheet is intended to remind you of very important things. Balancing equations can be tremendously tricky. Okay, so if we have this example here, I have manganese here, or magnesium, I'm sorry, and then I have silver nitrate. Okay, that is the AgNO3, and I'm combining them, and I get a new ratio of these elements. All right, this is a little bit complicated because NO3, or nitrate, is what we call a polyatomic ion. All right, and so this example, I'm going to do a little bit of background on it. But first, I'm going to talk about the number of atoms or molecules on the left and right, and the background with polyatomic ions. That's going to get into why I said number of atoms and or molecules, okay? So we've got one atom of magnesium on the left and one atom of magnesium on the right, okay? I can see that because there is no subscript for either of these, all right? Continuing on, all right, I've got one atom of silver on the left and one atom of silver on the right. Okay. And finally, here is the molecule. I have one molecule of nitrate on the left, but I have two on the right, hence the fact that this equation is unbalanced, okay? And so they wrote the equation based on the oxidation states of different elements and polyatomic ions, and that's how they ended up with the ratio of 1-to-2 on the right-hand side for magnesium nitrate, all right? So we have to balance this. We have unequal amounts of nitrate. What you're going to see is once we balance those, we might have other things to do as well, all right? But before we get into that, I'm gonna go and help you understand how this equation came to be in its current state, its unbalanced state, and that has to do with the periodic table. So if we go to the periodic table here, let me flip this, all right, we can see over here that magnesium has an oxidation state of +2, all right? We can also see that silver It is, where is silver? It's here. It has an oxidation of +1. Let me actually zoom in a little bit more and rewrite those so we can see a little bit clearly, a little bit more clear. All right, let me clear this. Now I'll circle this again. We got +2 for magnesium. We got +1 for silver. And if we remember from the crisscross method of creating ionic bonds, all right, we crisscross oxidation state for number of atoms. All right, so if I were combining these two, I would move the 2 down to silver and I move the 1 down to magnesium. Of course, we're not really going to worry about these because we don't deal with too many metallic bonds. All right. But in any case, you remember the crisscross method. So it's vital to know your oxidation states and how the unbalanced equation came into being. Now, this shows the 2 elements, but we also have to consider that polyatomic ion. And for that, we have to move a little bit farther back in our reference table. So I'm going to scroll up to this page, all right? And let me rotate this. There we go. Actually, I chose the wrong page. I think it's right here. Here we go. Table E. So this is page 2 of your reference table, and we have selected polyatomic ions, all right? So these are commonly occurring multiple element ions, all right? What I mean by that is that they have a charge, all right? They're not neutral, and they show up very often in nature. So it's very helpful to know them. And here we have nitrate, okay? Again, my clue for this is when I was looking at 2 molecules of that, there was a set of parentheses around it, all right? So I've got nitrate over here, and I see that it has a negative sign after it. That means that its charge is -1. All right, so I'm going to clear this. Now, you could balance this equation without knowing these things, but it is very helpful to know how we got to this unbalanced state. So we look for a pattern to multiply by once we figure out the number of atoms or molecules on the left and on the right. All right, so if we go down here, we can see that the only thing that is unbalanced is the nitrate right now. And so I have to multiply this entire AgNO3 by a number in order to balance this. So I got 2 over here, I've got 1 over here. So I'm going to multiply that by 2. And that's what I do in step number 2 right here. All right. I multiply AgNO3 on the left by 2. Now, that not only changes this NO3 here, but it has to change the silver that it's attached to as well. And so you can start to see how balancing equations becomes a little bit tricky. All right. Sometimes you end up manipulating the amounts of more than one thing at a time, which means that then you have to go back to the other side and make adjustments there too. So now these are balanced, all right? These NO3s are balanced. However, my silver, those are not balanced, right? Those are not balanced yet. So I only have 1 over here, not balanced. So I have to go down. And now I have to multiply the silver on the right by something, all right? So I'm going to clear this. And if I go down, I'm very relieved because all I have is a silver by itself. And so that's very easy to balance, okay? All I have to do is multiply that silver element by itself by 2. And now I have 2 moles of that on the right-hand side. And now everything is balanced, all right? I've balanced my magnesium already, my nitrate I balanced in my first step, and finally I rounded it out by balancing my silver, all right? And this brings me to my 2-step process here, all right? The first thing that I'm always going to do is I'm going to try to balance elements that are in compounds first. I try to balance those before I balance individual elements, all right? Before individual elements. And that's why I multiplied this whole thing, all right? Because I wanted to deal with a compound before that. The reason I want to deal with a compound before an individual element is that it's so much easier, as I showed you, it's so much easier to balance individual elements afterwards, okay? Then I go down and I balance individual elements accordingly because I just have to multiply one thing and I'm not worried about a domino effect of multiplying multiple things by a coefficient. Hopefully this cheat sheet is helpful to you. Keep the principles on the left-hand side of the table in mind, all right, as well as the explanations on the right as you're trying these problems. And we're going to try one more together. All right, again, you've got this guide to help you out. So let's take a look. I have a specific example I want to try. Okay, so let's see if we can employ my method here. We've got phosphorus and oxygen, and they're combining. If you recall, this is a synthesis chemical reaction, all right, because we're taking two elements, we're combining them to make a compound. Okay, so the first thing that I want to do is I want to realize that I have a certain amount of phosphorus and oxygen on each side, all right? So I'm going to make left and right here as the two columns in my table, and then my two rows are going to be for phosphorus and then for oxygen. I'm going to split here. Let me change colors so this pops. All right, we can see from this that I have 4 atoms on the left of phosphorus, and I have 2 on the right. So those are not balanced. Neither are the oxygens. I have, use a different color. I have 2 on the left and I have 3 on the right. Okay, so I'm gonna mark that in here as well. 2 on the left, 3 on the right. Now, using my principle to balance compounds before elements, I'm thinking 2 things. Number 1, all right, I need to balance both elements in that compound. However, the second thing that I'm thinking is there's no number that I can multiply 3 by and make it equal 2. Nor is there one number that I can multiply 2 by and make it equal 3. So since that oxygen situation is a little bit more complicated, what I'm going to do is I'm going to try to balance my phosphorus, because I know I can multiply this thing on the right-hand side by one number and get equal amounts of phosphorus on left and right. And then I can go and I can try to balance my oxygens, all right? So I see 2 on the left and 4, or sorry, 2 on the right and 4 on the left, which means I have to multiply the right-hand side by 2, because 2 times 2 equals 4, all right? So I'm gonna cross this out and I'm gonna replace it with a 2, okay? And that means that a couple things are gonna change, all right? For one, this is going to change to a 4, and now I have balanced amounts of phosphorus, okay? And now I'll note one other thing. That shouldn't have been a 0 in front, that should have been a 1 to start. Over here, that would have been a 1 initially, all right? I'm never gonna start with 0 moles of anything in chemical equations. Now, if I put a 2 here, not only am I multiplying that phosphorus by 2, but I'm multiplying the O3 by 2 as well. So 3 times 2, that's going to equal 6. All right, so I can cross that out down there. Now I have 6 over here. And now the situation is resolving into place. I multiplied my compound and I got into a situation where all I have to do is multiply one of my elements. And that is the oxygen on the left-hand side, okay? And obviously all I need to think to myself is 2 times what equals 6, or I can take the 6 and divide it by 2 and realize that I need to multiply this oxygen on the left by 3. Okay, so I'm going to do that right now. Cross this out, replace it with a 3, and now I can go here, cross out just my oxygen because I was just balancing an element, not a compound. And it looks like everything is balanced. Okay, so once again, guiding principles for chemical reactions. Balance your compounds before you balance your elements, or balance your elements in compounds as much as possible before you tweak individual elements in a chemical equation, all right? Make the table of how much there is of each element on the left and right-hand side of a chemical equation. And if you do those 2 things, you'll start to catch on fast. You'll start to see patterns in how you're going to multiply these things very often. And on the Regents, the last thing to say is on the Regents, very often they bring in similar level difficulty problems. So if you start to master ones that are about this difficult, for the most part, you'll be okay. We're not going to get too much more complicated. So I hope all of that was helpful, and I'm going to post this sheet along with the video. I hope it all helps you, and I will talk to you soon.